Okay, somebody asked me a question about these kinds of problems, so I thought I'd just go through this. So these kinds of problems are, what I mean by these kinds of problems are what they call limits at infinity. So you take some function like this, or like this, or this function, whatever, and we're asking what happens as x gets, this basically just means when x gets bigger and bigger. Okay, and here I guess, let's see, yeah, these are all here. When x gets smaller and smaller. So if we look at maybe a picture, let's go to here. Let's see if we have a picture of any of these functions. Okay, so maybe one of those functions looks like this. This is pretty strange looking function, but maybe one of those functions looks like this. So what we're asking anyway is, as x gets bigger and bigger, as we move this way, is there some number that the height is getting closer and closer to? So here, if this is 4, this must be 2. So here, as we move to the right, x seems to be getting closer and closer to 2. We say it's getting closer and closer to 2 from below 2, right? It's not coming from above 2. It's coming from below 2. But in any case, it's getting closer and closer to 2. Here, this one is getting closer and closer to 2 also. This time we'll say from above 2. But in any case, it's also getting closer and closer to 2. Now, they don't both have to, as you go to the right, it doesn't have to get closer and closer to the same number that it goes to from as you go to the left. In fact, you can have this one getting closer and closer to some number and this one not getting closer and closer to any number. But in any case, this one, as you go to the right, is getting closer and closer to 2. This one, as you go to this same graph, I guess, as you go to the left, is also getting closer and closer to 2. Now, if you looked at a parabola, remember a parabola looks like this, then as you get as you move to the right, it doesn't get closer and closer to any number, it just keeps going up, 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 up. We say then that the limit doesn't, we either say it doesn't exist or it goes to infinity. Sometimes we'll say it goes to infinity. So like a parabola, we might say goes to infinity. Okay, now one thing to remember about limits is if it does approach a number, not infinity, but a number, it has to approach a single number. So this one does seem to be approaching a single number. It looks like it's approaching 2. Remember, when we say it and we're looking at the picture, we mean the height of the graph. So the height of the graph is approaching 2. So we want to find out these values, like as you go to the right, is it approaching something? If so, what is it? And same thing to the left. So those questions are asked by saying as x approaches infinity. In this case, it's not x, it's t, but as x approaches infinity, or as x approaches negative infinity, and we want to answer that question. And also, by the way, if you have a number that it does approach, then we call this red line here, we call it a horizontal asymptote. Okay, this red line, if it that line that it approaches is called a horizontal asymptote. Now, it doesn't just to be a horizontal asymptote. If we go to the right and it approaches something, that's enough to call something a horizontal asymptote. It doesn't also have to go to the left and approach that number. So even if this part weren't here, or it didn't approach this, still, we'll call this red line a horizontal asymptote. Okay, now let's go back to here, and here. So limits at infinity. Compute the following limits if they exist. So here's a question. We're asking what happens as you go to the right. Is there a limit? Is there a single number that the function approaches? Is there a line that it gets closer and closer to a horizontal line? Same thing here. As we go to the left, is there a horizontal line? Go to the right. Is there a horizontal line? Go to the right. Is there a horizontal line? Go to the right. Go to the right. Okay? So how do we do these? So actually, we didn't really talk much about it. It says solutions A and B. When calculating the values of the tables, for the tables used in example 3, you might have noticed that the highest power in x in both the numerator and denominator dominated the calculation. So, okay, so I don't know. You can go back and read this, the tables in example 3. I'm not going to do that right now. What they're saying, though, is there's a way to do this, a kind of easy way to do it. What they're saying is that the answer, if you start to put in values for x, like put in 10, put in 100, put in 1,000, put in 10,000, put in 100,000, put in a million. In other words, let x get bigger and bigger, and look at this. You're going to see that the most important terms here, there's 2 terms here and there's 2 terms here. Which of them are most important? The terms with the highest powers are the ones that are most important. So x squared and x squared term, x squared and x squared term, x squared and x cubed term. Those are going to be the most important. That's what they're saying. So let's go to the next page. So let's see what they say here. In other words, for large values of x, this thing basically behaves like this. In other words, this term and this term are not really important. And so we can say that it basically is the same as just this term and this term. Therefore, they suggest that the limit for this, if it's plus or minus, they're saying, is basically the limit of this. And then the limit of this, what can we do? We can cancel the x squared and the x squared. And so we're just asking for the limit of 2, and that is equal to 2. Okay, now you can check this video. And let's go to here. So let's do something similar here. So the terms that dominate, again, they suggest are minus x cubed and 2x squared. So they say the limit of this is basically the limit of this, or is the limit of this. And then here we end up, when we do the cancellation, we get minus x over 2. And as x goes to infinity, what happens to this? This just goes to infinity. Goes to minus infinity, actually. So they write this is minus infinity. Okay, let's go to the next one. The terms with the highest powers are this and this, this and this. Canceling, we get this, and then then letting this term x go to infinity, you get 0, so the whole thing goes to 0. Okay, now the next one, here we do not have a ratio of polynomials, right? These were ratio. This is a polynomial, and this is a polynomial, so this is a ratio of polynomials. This time, in this example, we don't have 2 polynomials. They say, however, we know that as t becomes large and positive, in other words, when x goes to the right, so does this. This also gets larger and larger and more positive. And hence, this minus 20, if you're just subtracting 20 from something that's getting infinitely large, you still get something that's infinitely large. So we get plus infinity. And let's see, the next one was here, I guess. So as t goes to infinity, this thing, is that minus t? This thing is equal to this in the denominator being 1 divided by a very large number, right? 1 divided, this thing gets bigger and bigger. So this is going to 0, right? So this is going to 0. Hence the denominator, this part here, is going to 1 plus 2 times 0, which is just 1. And so on the top we have 80, on the bottom we have 1, so we get 80. Okay, before we go on, now look at the graph of the function, this one, in parts A and B. I guess that's maybe this one. Is that this one? I'm not sure, but anyway, we say that the graph of f has a horizontal asymptote at y equals 2. So maybe this one, y equals 2, because the limits we have just calculated. So I guess we just did this, and we got 2 to the right and 2 to the left. This means that the graph approaches the horizontal line, this horizontal line, y equals 2, far to the right or left, in this case, both right and left. Figure 19 shows the graph of f together with the line y equals 2. Let's see. Anything else here in this section? Yeah. Okay, the graph reveals some additional interesting information. As x approaches 1 from the right, f of x goes to minus infinity, and as x approaches 1 from the left, f of x goes to plus infinity. Let's just take a look at that picture again. So as we approach 1, here's 1 from the right, I guess. We go to minus infinity. As we approach 1 from the left, that's going this way, we go to plus infinity. As we approach negative 1 from the left, we approach negative infinity, and negative 1 from, I said that wrong. As we approach negative 1 from the right, we go to negative infinity. As we approach negative 1 from the left, we go to positive, no. Something's wrong with this graph. It's not drawn right, I think. Maybe I'm wrong. Let's check. What is this graph? What is this function? Oh, here. This one, right? I guess it's this one. Is that right? This has, if you look at this, when is the denominator equal to 0? When is this part equal to 0? It's when x is 1 or negative 1. So when x is, I don't think this is the same as this. No, I'm sorry. This is right. I was thinking this was 1, but this is not 1 here. This is 1 here, and this is 1 here. Okay, so it is right. I'm sorry. So anyway, here this has the denominator is 0 when x is 1 or negative 1. So usually that means, not always, but many times, or sometimes anyway, that means that you're going to get a vertical asymptote at 1 and negative 1. In other words, as you approach 1 from the right, you might go to a positive or negative infinity. From the left, positive or negative infinity. As you approach negative 1, you might get positive or negative infinity. Okay, it doesn't always happen, but sometimes that happens. So let's go back to there. The graph reveals some additional interesting information. As you approach positive 1 from the right, it goes to negative infinity. As you approach positive 1 from the left, it approaches positive infinity. So first of all, since they are different, as you approach from one direction, you get positive infinity, and you approach from the other direction, you get negative infinity. So one of these is negative, one of these is positive, and we say the limit doesn't exist, because in order to say that it exists, you have to get the same thing from both sides. We've said that before. See if you can determine what happens as x goes to negative 1. I think it will say it's exactly the same thing. The limit doesn't exist. If you graph the functions in part D and F of example 4, you will again see a horizontal asymptote. Okay, so you can check that. It's worthwhile looking again at what we did in each of the limits in example 4. Okay, let's take a look at that. So just to review, we saw that this was approximately equal to this, and then we canceled the x squared. Notice that before canceling, if we had just let x go to infinity, we would have gotten infinity over infinity. The numerator and the denominator yields the ratio infinity over infinity, which similar to 0 over 0 is what's called an indeterminate form. It means we can't really say what it is. Okay, so if what we did was we canceled the x squares, but if we hadn't done that, if we had instead just put in infinity on the top and infinity on the bottom, we would have gotten this, which is similar in some sense to this. It's called an indeterminate form and indicates to us that further work is needed, in this case cancellation, before we can write down the limit. In this one we obtained this, which results in another indeterminate form, minus infinity over infinity, as x goes to infinity. But what we did instead was we canceled first. Cancellation of the x squared gave us this, resulting in the determinant form, this over this, which is that. Okay, so this one is called indeterminate. We don't know what it means, but this one we do know what it means. It means minus infinity. And same with other things. Excuse me for a second. Okay, so we get that. All right, so that's enough for this. And you can read these. Okay, one more. I guess we don't usually cover this, but let's do it. We don't usually have time to cover all these things, but I'll just mention it here. So here we're talking in general, generalizing what we just did, what we just looked at. What I mean by that is when we have a polynomial on the top, this is a polynomial, right? X to the n minus 1, all the way down to like a constant term. And this is another polynomial on the bottom. So how do we generally, what's the general procedure for dealing with this? We take the highest power here and the highest power here and ignore all the other terms. Okay, so the limit of this thing is just the limit of the two highest power terms. So that's the Cn x to the n over the dm x to the n. Okay, so that's a generalization of what we did so far. And what else? So here's some examples. So you can look at those. And here's the proof of that theorem that we just looked at. So what they do is, just to quickly explain, what they do is they take the highest power. So if x to the n is higher than x to the m, for example, or vice versa, but if x to the n is greater than x to the m, they divide everything by x to the n. So this one divided by x to the n, this one divided by everything divided by x to the n. And what you end up with is what? This term just becomes what? C to the n, and all the other terms will have an x in a denominator, x in the denominator, x in the denominator, x. And when x goes to infinity, what happens to all these other terms? This goes to 0, this goes to 0, this goes to 0, because they all have an x in the denominator. This one does not go to 0. All the others go to 0, so you end up with c sub n. Okay? And you can check that. So we're not going to go through all this stuff, but you can read it. It's about determinate and indeterminate forms. Okay? All right, that's all.